Right, hello everybody. My name is Cyrus. This is the re-recording of my talk, Prompt Engineering is Dead, Long Live Prompt Engineering, for Arize Observe. And we're gonna go through this with you now. Ooh. There we go. All right. So this was originally presented at Arize Observe in the morning, so I asked everybody to say good morning, raise their hands up. If you're seeing this, you're sitting at a computer, raise your hands up to your head. Take a good stretch the back. Oh yeah, look at that. This is wake up. It's a beautiful day. And then I went around asking folks who was an ML engineer, who was a software engineer, PMs, founders. We had a good variety of everybody, at any moment, 20 to 40% of the hands were up. And I wanted to start off by giving you some context on who I am. My name is Cyrus. I've been an autodidact since forever. I've been a full stack developer for the last 12 years, working in early stage startups. I've created a generative AI app that got 100 million downloads, and last year I started doing multi-agent systems research at Camel AI and Noose. I'm a major contributor to DSPy, and right now I'm the co-founder of Zenbase, which we're grateful to be in YC's latest batch. So what are we going to talk about today? This talk is split into 5 parts. A day in the life of a prompt engineer, automated prompt engineering, intuition and efficacy, APE for ML teams, and then APE for product and engineering teams. There was room for Q&A at the end. We went over time, so during this re-recording, I'll go through some of the supplementary materials instead of a Q&A. And I want to start off by telling everybody to be curious. Curiosity is what helps us adapt to new things that we've never experienced before. Curiosity is how we tinker and fiddle with language models and create amazing things. So throughout this talk, I want to encourage you to be curious, and also in general, for the near future. So let's take a look at what life is like being a prompt engineer. You start off with some loose understanding of what you're trying to do. You write a prompt, you test it out a few times, you check the vibes on 3, 5, maybe 10 examples, and then you go back, you fiddle with the prompt, you try it again. Maybe you think about certain, edge cases that you definitely don't want this to handle, so then you start adding some guards, and really what you're trying to do here is iterate towards a better design. This diagram on the right over here, very important diagram. You're starting off somewhere on this landscape, and you are gonna fiddle with your prompts, run it a few times, see how it works, get that vibe check, and get it to somewhere that's better. If you want some additional reading, by the way, we highly recommend this what we learned from a year of building with LLMs. And so what happens if you get a little bit more sophisticated? Okay, now you got some evals in place. Maybe you're using Arize Phoenix to do experiment tracking, or one of the other platforms that are out there, like Langsmith or Langfuse, and weights and biases we've recently. But fundamentally, you're still doing the same thing, which is fiddling with the prompt, running some experiments. Now you have something a bit more quantitative that you can look at, but it's still this trial and error process for traversing this landscape. And everybody's experienced this when they work with language models, and you're not alone. This is just how things are right now. There haven't been particular tools that help you with traversing this landscape of what possible prompt you put in so that you can get the right thing to come out of the language model. And this really sucks, right? It requires a new mindset versus the programming that we're used to as engineers, where we can be very clear about how things work, we can assert how things are, and we can throw an error. And when we write our function and we test it, we know it's going to work basically 100%. Here, that's not really the case. Now, you might go and set up some automated evaluations, but these are just vibe checks at scale, because they capture a certain quality of the output, but they don't give you that certainty. And not only that, but your definition of good evolves over time. So the evals that you may have on day one are not going to be the evals you have a year in or a year later. It's a year after that. So how do you systematically grow and develop and improve your system? Not only that, but there's all these tricks over the last year. We've heard all these tricks about what magic words to whisper to language models to get them to say what we want them to say. Take a deep breath and think step by step. I'll tip you $500 if you'll do this for me. First plan and then check your work. What all these different things. It practically requires one person just to keep up with all the stuff that's coming out these days. Not only does prompt engineering suck for the person doing the prompt engineering, but it also sucks for the team, because prompt engineering is a massive, uncertain time suck. You don't know if you spend 4 hours on this thing, whether you're going to come out better on the other side or not. It's really, really challenging. And I have this funny graphic here. Changing random stuff until your program work is hacky and bad coding practice. Yes, it is. Yes, it is. This is the challenge we're all facing. So, let's talk about what can be better. And to do that, let's develop some intuition about how this works and how effective these systems can be. So you might remember this meme I put on the last slide. And if you try a bunch of different things fast enough, it's called machine learning. So what if we could have the AI try different prompts for us to find out what the best prompt is? And that's what automated prompt engineering, or APE, is really all about. It's finding intelligent ways to search through what are the useful prompts, or the best prompts, or the good prompts, and do this for you. Do the prompt fiddling for you so that you don't have to do this. And people are using this to create these more complex systems, like the ones on the screen, like the ones you probably have at work. And with all the different prompts that are out there, it's really complex trying to figure this out by trial and error by hand. So this is where APE can really help, because it will fiddle with the prompt for you in an intelligent way. Let's go to the next slide. If you're coming from machine learning, I have some analogies that are gonna help you get up to speed really quickly. And if you aren't, then I'm gonna translate it to make it easier to understand. In the world of machine learning, we map numbers to numbers. We change numbers, we did stuff with numbers, and then we got numbers out of it. In the world of language models, we have text to text. You might be taking some text and summarizing. You might be taking some text and generating an answer. You might be taking some text and classifying something. So we've moved from numerical transforms to text transforms. Another topic that is very prevalent in machine learning is this concept of a loss landscape. You say how bad an answer is, and depending on how you fiddle with, or how the optimizer really fiddles with the weights and the biases and the numbers inside the machine learning model, you can map this landscape out and figure out where minimizes the loss, gives you the least bad answers. And when it comes to APE, we have the inverse of this. So we have what we're calling a metric mountainscape, where we're trying to maximize a metric. And depending on what prompt you put in, that metric will there will be a different number for that metric. And just like how in machine learning we had algorithms like ADAM, or a stochastic gradient descent, for navigating that loss landscape, in APE we have algorithms pioneered by DSPy that help traverse this metric mountainscape. And so we're letting the computer go through the possibilities, the search space of what prompts are good prompts for us, so that while it's doing that, we can go out to lunch. While it's doing that, we can focus on creating value for our users. And APE can be really, really efficient. The first thing over here is a study that was done in collaboration with Microsoft and OpenAI, I believe, where they had one expert prompt engineer try 49 different prompting techniques Then they had one ML engineer use ape and then also tweak it a little by hand at the end. And they found that after 20 hours of the human prompt engineer spending this, he couldn't beat automated prompt engineering. Automated prompt engineering did 40% better than the human prompt engineer spent 20 hours trying 49 different techniques. The great folks at Hayes Labs in the center diagram, they created a model for red teaming language models to hack them, to jailbreak them, to get them to give out a harmful response. And they created this architecture. They optimized the architecture with DSPy, and they found that the optimized form performed 69% better than the unoptimized version, which did itself like 160% better than just writing one prompt by hand and being like, okay, hey, can you check to see, can you come up with something that's going to hack the LLM? And in a more academic setting at the bottom over here, we have Wang Lab, a team out of the University of Toronto where I grew up. They had a model that worked on the MetaQA data set, and they used DSPy, they used automated prompt engineering. They blew everybody else out of the park, and you had PhDs writing prompts for you. And PhDs with automated prompt engineering got 20 percentage points better than the next best PhD who didn't use automated prompt engineering. People are already experimenting and prototyping with automated prompt engineering. Some big names that maybe you've heard about on the right. So now I stopped for questions. One question that came up is going to be answered soon. So if you're an ML team, how do you take advantage of automated prompt engineering? Well, I would highly recommend DSPy because it's fantastic. If you're coming from an ML background, it maps to how you might think of the world, and it gives you a PyTorch-like interface for working with it. DSPy is the hard work of all these contributors on the right who, it's the sum of our work and more. And DSPy, great project. It's recently became Stanford NLP's #1 GitHub repo. How does it work? Well, sort of like a PyTorch for LLMs, like I said. And you have some module here in the middle, and then you can create a optimizer here. It's called a teleprompter, but it's really an optimizer. And then you can compile your module over here. So you have this module, it's like a model. Like it does stuff, and it has some language model transformations. Here, this chain of thought question to answer, it says, hey, I'm taking a question, I'm giving an answer. And we want to optimize this question to answer system with a teleprompter or an optimizer to perform well on the learning set and the eval set. Notice how we don't write a specific prompt here, but rather we're using an optimizer to figure out the best prompt for us. And to take advantage of this, you need a learning set, you need an eval set, and you need an eval metric. These are the three things to take advantage of the optimizers in DSPy. And all those previous examples I gave are examples of DSPy being used. People are doing amazing things with it, and we hope you will too, and we'd love to help you do that. We're going to go deeper into DSPy. I would recommend checking DSPy's tutorials out, the website out, if you want to learn more about that. We're going to go deeper into how it works in the supplemental materials at the end. But do check it out if you're an ML team interested in automated prompt engineering. So what about product and eng teams? Well, they have different needs. They are typically in a continuous development cycle where they're releasing every week or every few days or every day if you're really good at it. Versus MLE teams, they might be experimenting for a while, they come up with something, then they figure out how to deploy it, and then it's more of a release cadence. MLE teams work in Jupyter notebooks and MLflow and Software engineering teams may be working in Django or Node.js. So it's very different. And software engineering teams have different mental models. They come from product engineering, they come from full stack engineering. They may not be as familiar with machine learning as machine learning engineers or AI engineers are. And for a machine learning engineer, success often can look like, okay, I got this working on the data set I have and it's working great. But the reliability and the scalability of it in production is not part of your area of concern. That's somebody else's problem. So software engineers typically, or ML ops people typically have to deal with that. So what we're trying to do at Zenbase is bring automated prompt engineering to product and engineering teams. So you can focus on programming and not prompting to ship better experiences faster for your users and create more value. We're starting off with a library called Zenbase Core, and this addresses one of the challenges that we found with certain teams that were curious about automated prompt engineering but couldn't afford a rewrite into DSPy to take advantage of it. So Zenbase Core provides DSPy's optimizers on their own in a way that lets you leverage them with your existing Python program. So your Python app, you may be using the OpenAI SDK, you may be using Instructor, you may be using LangChain, you might have a chain, a LangGraph even. Zenbase Core works with all of those. You don't have to rewrite your app to optimize it. You can take what you have now and optimize it. And this is what we believe to be the first shot at the optimization layer for the AI stack, where different systems and even libraries or domain DSLs can leverage what we're working on Zenbase Core to provide the best performance to their user. It's over here. I have a function which does some very basic things. It's got a list of messages, and then it's calling OpenAI, and it's trying to do some math. And I want to bring attention to two things in this function. Three things. The first one is this def-lm decorator at the top. Then it's the input. There's this LM request argument being passed in. And then there's this loop where it says for demo in request.zenbase.taskdemos. So what's going on? Well, the Zenbase Core optimizers will pass in certain params into your function that then those variables you can inject into your prompt. And we're going to find the best variables to put in. So the root of all this optimization is what are the best few shot examples or the demonstrations for the task. That's why we call them task demos. We'll find the best task demonstrations for few shot prompting and in context learning for you to put in your prompt how you see fit. So maybe you're using JSON mode, you need to dump the JSON, you can do that. Maybe you're using cloud and you want to put it in as XML, you can do that. We'll figure out the best examples and demonstrations to pass in and what order they're in, and then you inject them into your prompt. Future optimizers also that have already been implemented in DSPy but not yet in Zenbase Core, they also optimize the instructions. So at the top here you see, you are an expert math solver. You must answer the question with your answer must be just the number. This is an instruction. So we can also figure out the best instruction to go in there to maximize the score of this function. And this function here right now is using OpenAI. You could be using LangChain, you could be using Instructor. Any way you want to call language models, that's cool with us because we're just going to pass into you these certain the Zenbase params and variables. And then you get the inputs as well, the request inputs, whatever params were originally are passed. When you call the function, we call those the request inputs. Then in the bottom cell, you import one of our adapters. We have adapters to work with Langsmith and Arize Phoenix and LangFuse and Lunary so that you can view the results of your experiment in a UI. We're not performing any black box optimization. We're trying different prompts out for you so that you can go into the UI and see what prompts are exactly being used. And then when you run the optimizer at the very end, you get back a function that performs the best. It's figured out. We figured out what the best Zenbase params are, save them with the function so that when you call it in the future, we've already got the best variables to inject. And we're working on something I would like to call Kaizen, which is how do we continuously improve your language model functions for you. Really exciting stuff. If you're curious about it, would love to talk about it. I also want everybody to know that you're early. This automated prompt engineering stuff didn't really exist 2 years ago, and only started coming around maybe a year and a half ago, and really hit an inflection point over the past 6 months. So we're still early, you're still early. There are a lot of rough edges, but this is what's coming. And we need to be prepared for how to think about our language model applications in the future, given that this is how I believe we'll be building them. I would love to talk to anybody who is dealing with errors, costly errors. If you have a classifier and you want to minimize your errors on that, would love to talk to you to help you out. If you have a pipeline or an agent flow and too many errors, or you want to make it better, you really care about reliability, would love to talk to you. If you're a DSPy user already with feedback, hit me up. If you're a product and eng team, or you have an interesting idea, or you just want to do something together, I would love to talk with you. Now, I think it's time for some of the supplemental materials. Now, you might be asking me, Cyrus, how do these optimizers work? Well, the root of all these optimizers is figuring out what the best few-shot examples for in-context learning are. These make the biggest difference in helping a language model generalize to a wide variety of cases. So, given that we can't just put, if we have a data set, a training set of like 1,000 or 500 or even 100 good examples of how this language model ought to do what you're asking it to do, how do we find the 5 best ones or the 10 best ones to put in the prompt, and in what order, so that this function works as well as it can? That's what labeled few-shot essentially does. So you have a training set where you've got these 100 examples, and it'll sample sets of 5 or 10 or however many K you configure, put it in the prompt, run it on your validation set, see what the score is on that evaluation set, save that, and then try all these different samples, try all these different subsets, compare all their scores, and then give you back the one that's the best, whichever one performed the best. You're like, okay, but how do you evaluate it, Cyrus? How do you evaluate whether it's a good answer? Well, if it's a classifier, you can just make sure that it's the right answer. Otherwise, you can, if it's more open-ended, which most cases it is, you want to maybe have an LLM as a judge. Maybe you want to consider multiple criteria, in which case, is it helpful? Is it not harmful? Is it concise? Each one of these could be zeros and ones, and then you sum them together. And, a score of 3 is the best score then. So you could even do something like that. Now, the basic optimizers start with how do we put the best few-shot examples in. There's a more advanced optimizer called MePro, and now there's a MePro v2, where at a high level, you got a pipeline. It'll run your pipeline end to end and save successful runs based on your eval score. And when it saves the successful runs, it saves the inputs and outputs of all the different steps in your pipeline. Then we use an LLM to look at the inputs for specific functions and summarize the patterns in the data. Then, based on the examples and the summary of the data set and the current instruction, do this math, we'll use an LLM to generate more instructions, more candidate instructions, and test those. So maybe, one thing they found is if you go ahead and say this is a calamitous situation, the species is about to go extinct, then the LLM works better at helping you figure out to classify the species. There's a Bayesian optimizer here to figure out, okay, what's the best combination of instruction and few-shot examples, and this can run in tens of minutes tops and costs like 10, 20, tops $50 in OpenAI costs, and save you hours of time. And I think that's it. All right, well, this was it. Thank you very much for listening to my talk on prompt engineering is dead, but long live automated prompt engineering. This has been Cyrus. Super excited for the future to come.